everybody. I think this might be the first time in my life where I am not the most polemical speaker at a conference. Exciting for me. So I'm aware that not all of you are musicians and not all of you are mathematicians, and so I'm going to be speaking a little bit in two separate foreign languages. I'm going to do my best. I just encourage you to try to zoom out, don't get obsessed with the details, and focus on the big picture. So the fundamental claim that I'm going to be making is that music involves motion on simultaneous hierarchical levels. These levels are sometimes called scales, chords. Some theorists have called them alphabets. And that once you see this hierarchical picture, a whole lot of things come into focus. So this is a picture from my new book. And at the top level is kind of the highest level alphabet. This is the level of the chord. And basically what happens is that musicians make patterns, in this case, patterns that can be expressed with these numbers up here, like +1, -1, +2, -1. So +2, -1. I have a very small keyboard, so please excuse any mistakes and infelicities. So that's the +2, -1 pattern up at the top level. We call it arpeggiation. Then below that, sort of that collection is embedded in a larger collection. And you can think of each collection as a kind of mapping between its input numbers and its outputs. So below that we have what's called the major scale, and you can do the +2, -1 pattern on that level. And then that same pattern is repeated, and it also has outputs at what we call the chromatic level. And that's the +2, -1 pattern there, okay? So if you were implementing a scale computationally, you'd want to make it a recursive nestable object. And I've done that. If you want to play around with it, I have some Python code that you can download that does this. So all of this is very simple, but it gets quite complicated when you have motion happening at all of these levels simultaneously. And then the other exciting thing about music that makes it different from mathematics is it happens in real time, right? So we have to manipulate this structure, which is relatively easy to manipulate with pen and paper. We have to manipulate it while we're improvising, while we're listening, and so things that, you know, might not be super complex from the standpoint of advanced mathematics become complex when they're being embedded or embodied musically. Now, since we're talking about scaling, each of these levels has its own time scale, all right? And just to give some back-of-the-envelope calculations, the Mozart's piano sonatas are 305 minutes long with repeats, so it's about 200 minutes if we take out the repeats. The sonatas contain about 100,000 notes, so something like 8 per second. That's the top level of motion. And then there are about 10,000 chords, so about 1 per second, and about 400 key changes, so those occur about 2 per minute. So we have these nice order of magnitude timescales that's happening there. And then each of these layers gives rise to specific musical phenomena. So up there at the top level, we have what I'm calling note dissonance, which is a kind of musical tension that is caused by notes moving from outside the chord into the chord. So, okay, so in that case, we're getting a little bit of a sense of tension and release by a melody that is moving from unstable notes that do not belong to that top collection and then away and back. We have another kind of dissonance that is caused by chordal motion, where the chords might be moving away from and back to a stable chord, and that's happening on the phrase level, so, 10 seconds. Each phrase is about 10 seconds long. Connected to that, we have a higher level melodic dissonance that has to do with chordally supported notes moving from more stable scale degrees to less stable scale degrees. And then finally, we have another phenomenon where keys are moving away from home and back to home, and that's happening at the level of the piece. And there are some actual interesting questions about the extent to which this highest level of motion is perceptible by ordinary listeners who don't have absolute pitch. So putting that all together, we get these 4 levels of dissonance happening at 4 different time scales: note dissonance, chord dissonance, melodic dissonance, key dissonance. And you might ask, well, sort of, to what extent is this Western? To what extent is this non-Western? It's really level 2B that is closest to being a musical universal. You find level 2B in lots and lots of different musical cultures. 1, 2A, and 3 are more particularly Western and have to do with a particularly Western way of conceiving the space of musical possibilities. Now, I have a little website where I generate fake music. So let me see, I had this all booted up and now it's not booted up. So I got to redo that. So just so you can get a sense for this, you can go to madmusicalscience.com and here's some artificial music. And what you're going to hear is really unutterably simple. It is just a sequence of descending 2-step scalar intervals. It's basically that over and over again. And all I'm going to do is change the scale on which that pattern happens, grab consecutive notes and turn them into chords, and occasionally decorate one of the notes with a nearby out-of-chord note. And you're going to get something that is not great music by any means, but should be recognizable as the kind of thing you hear in Baroque and classical music. Let's play. Okay, so there's about 25 lines of code, and I guess one thing that you can say is like the secret of Baroque music or classical music is it's actually not that hard, right? That's the core engine of the music, and then you make melodies and you express yourself and you do human stuff on top of that. But that simple 25-line algorithm takes you a lot of the way toward the genius and the amazing miracle that is classical music. All right, so from a scientific point of view, the collection dependency of musical motion is a real obstacle to quantitative and computational musical analysis because audio files give you no information about what's going on. MIDI files contain only chromatic notes, so I see a lot of quantitative analyses of music that are just using the wrong distance measure because they're measuring things only in terms of steps on the chromatic piano keyboard, and that's not the syntactically relevant notion of distance. Even musical scores don't represent collections in any kind of perspicuous or obvious way. And this is actually something that I'm working on. I would also make the conjecture that, so I think machine learning works amazingly well for visual images and works sort of somewhat okay for text and just is terrible when it comes to music. When I hear AI music, it's not even remotely interesting to me. And I think the reason for that is there just isn't enough data in any one style for machine learning algorithms to do much more than pick up the rudimentary basics of this kind of structure. And if that's right, that suggests a way to fix it by generating artificial data that has the appropriate structure and then sort of pre-training your model artificially and then maybe finishing it off with actual music. So that's an interesting project. All right, so that's my big picture. Now I want to give you a couple of, what you can do with this. First idea is this hierarchical picture gives you a new approach to melodic analysis, and we're going to illustrate starting with this little Mozart melody. focus just on the beginning of the melody. And this melody has two parts, two halves that are sort of parallel. And the interesting thing is if you asked any scholar of music to, a music theorist, if you asked them to analyze the melody, they would circle the three notes that I've circled here and say, those are the skeleton of the melody. Three blind mice. Three blind mice. Okay? And in fact, just to test this, I had my friend Poundy Burstein. I had him send me an analysis of this little phrase. He sent me this thing up there, and you can see his three blind mice with a little 3 right there. Now, if you're a human being who's not been, not received a PhD in music theory, this looks really dumb. And the first reason it looks dumb is it's asymmetrical, right? The analysis takes the first part of the first motive and connects it to the second part of the second motive. But the two boxes are like copy and paste transformations of the same structure. So on the surface, it looks kind of weird to take the first part of the first structure and the last part of its copy. Why on earth would you do that? The other thing is that the analysis emphasizes a kind of descending motion across that little phrase, when in actual fact, the little pattern moves upward by one scale step, right? So it looks like the PhD music theorists are doing something very unnatural and very contrary to the manifest image, the surface of the music. And if you asked me 5 years ago, I would have said, that's because they're dumb. Well, in those 5 years, I've gotten a little smarter, and they've gotten a little smarter too, correspondingly. This analysis makes a lot of sense if we think that a chord can act like a little scale. So here I've given you an analysis of that phrase where I imagine that we basically have this collection as our top level alphabet, and it moves down. It just moves down like a very small scale like this. And you see time progresses downward in this graph. If you analyze the music in this way, you realize that it's actually presenting two different kinds of intervals, two different kinds of motion, which I've color-coded for you. The blue ones are motions within an alphabet. And then the alphabet itself shifts down. And so the red arrow is not produced by motion relative to that top level collection. It's actually produced by motion of that top level collection. And so the melody, the analysis you get, there's no mysticism here, you're just treating chords as little scales, you get something that looks like this, and then it turns out that the standard music theoretical analysis is actually correctly tracking the progression of this voice. Here, we can listen again. So I would say that this is not, in fact, dumb. And what's going on here is that melodies generally have a two-level structure. They contain motion attributable to underlying chordal voices, which typically happen slower. I call those things threads. And then we also have motion between threads, which is motion of, say, a single note relative to this fast-moving chordal structure that I'm coding as blue. And so here you see the red motion there. And then the interesting thing is that you often have these little bits of recursive structure, right? So here we have the three blind mice happening in red, and then we also have a fast little three blind mice happening in blue quicker, and that's also present in Poundy's analysis that he sent me up there. So you often hear people talk about the recursive or quasi-fractal nature of musical melodies, and I think it's coming from this structure. Once you realize that chords can be little scales, you start to find all sorts of manifestations of this pattern. Here's one.
What would you think if I sang out a tune? Would you stand up and walk out on me? Lend me your ears and I'll sing you a song, and I'll try not to sing out of key. Oh, I get by with a little help from my friend. I get high with a little help from my friend. Gonna try with a little help from my friend.
Okay, I don't have volume control. I apologize by that. I thought I did. Okay, so again, here we have 5, 4, 3, and you can see the red pattern also embodied in the blue pattern. Another thing you often see is surface voices moving contrary to this background level. About 5 years ago, I was soundly sleeping, and at 2 in the morning, I sat up bolt upright, and I said, holy shit, how did I never notice the ascending thirds in the Waldstein before? And then I said, excuse me, what? And I sort of sleepily sang through the opening of Beethoven's Waldstein Sonata and realized that there's this underlying pattern of ascending thirds that goes through the entire gesture. So this is an example where the background level of chords is kind of sinking downward. That's what's happening here. And the melody is rising against that. And that's the kind of math nerd stuff that Beethoven really loved. Once you get to know him, you realize he's doing this all the time. I have a little movie that exhibits this. Again, time goes downward here, and what you'll see are the 2 notes that the melody focuses on gradually ascend rightwards as the piece goes on. Okay, so my first claim is melodic structure really only becomes truly clear once you start seeing it in this hierarchical fashion. The next thing I want to talk about is voicing and motive, or what you can think of as musical patterns. What is a musical pattern? I would say the notion of chordal inversion is central to the concept of a chord, but musicians don't understand it very well. One of the wonderful things about music is musicians have a tremendous amount of knowledge, but it's trapped away in our bodies. It is not accessible to language and conscious sort of formulation in terms of rigorous concepts. Inversion, in my worldview, is just motion at this top level of the chordal hierarchy. So for those of you who are not musicians, just ignore this. Those of you who are musicians, we form inversions by taking objects and moving them along the top level of this hierarchy. Big deal. Okay, what we call a motive or a musical pattern is essentially a chord that's been outfitted with rhythmic structure and a hierarchical set of distances represented by the arrows on this hierarchical diagram. And this is really interesting because rigid translation of musical patterns does not sound like rigid translation to the ear. So here I have a kind of very simple motive. Simple little jazz motive. Every jazz player knows what to do with that motive. Almost no one educated by classical musicians or contemporary super sophisticated art musicians knows what to do with that motive. What you do with that motive is you drag it along the top level, and these arrows update themselves accordingly. So in its original form, it sounds like that. And then if I drag it to the left by 1 position, it sounds like that. And if I drag it to the left 1 more time. So I've tested this on my students who are jazz musicians, and I say, okay, here's the original. Can you play it some more forms for me? And they come up with these things reliably. And I test them. I say, well, what if I make this a D flat? And they're like, no, that's wrong. It doesn't. And I say, how come? They say, I don't know. It just sounds wrong. So what's really interesting here is there is an algorithm. The algorithm is not one that can be expressed in terms of MIDI notes or found if you're looking at audio or even necessarily found if you're looking at the score, but there is an algorithm there. And I wrote a little computer language because it gets, oops, what just happened here? Oh, I see, hold on. I gotta get out of PowerPoint and go to the, okay, right. I wrote a little computer language for manipulating musical patterns. So this is a language, it's called ARCA, a pattern language for music. This is a bunch of computer code. It uses my Python library for hierarchically nesting different musical objects. I've loaded up a preset called Beethoven Opus 130. So this is a little episode from a late Beethoven quartet, Opus 130. It's not note for note exact, but it could be made note for note exact. Let's just listen to the sound of this computer code. All right, so this is interesting because we don't think of Beethoven as an algorithmic composer, but in some sense he is an algorithmic composer. This is the algorithm.
So you started with the Beethoven theme,
yes,
and then you transferred it with your code.
Yes, I modeled Beethoven's music using my code.
But you started with his music?
Correct.
You didn't say that. Yeah.
So an interesting question is, can we infer the code? It's called program induction. Can we infer the code from the music? I did it by hand because I'm a musician. So as I was saying, Beethoven is not thought of as an algorithmic composer. You can do this kind of thing for Chopin. You can do this kind of thing for Mozart. You can do this kind of thing for the Beatles, right? Not all music is this algorithm, but this algorithmic, but a lot of music is, and a lot of parts of music are. So it's maybe like the optics, to use a metaphor, that these composers were using. It's their secret trick. Okay, so actually one cool thing is I have a student who has embedded this kind of theoretical knowledge in what's called a DAW, a digital audio workstation, which is the primary tool for recording, film music creation, and so on. We've applied for a patent. It's quite possible that in the future, this way of thinking about music will be built in to lots of different kinds of music software. We don't really want to make a lot of money off this idea. We just don't want Apple or Pro Tools to steal our idea without letting us work on it. Okay, application 1, melody. Application 2, pattern. Application 3, repetition and symmetry. So music is all about repetition, and repetition is the application of a symmetry transformation. The first and most obvious is time translation. That's enough of that. Time translation gets kind of boring after a while. Another symmetry combines time translation with pitch translation, and we call this a sequence. Each time it repeats, it moves down one level, and that makes it sound a little more interesting. Another kind of variation or asymmetry is to move the lines from one instrument to another to permute the instrumental assignment, and we call this a round. Okay, kind of amazing how much of a difference that makes. That's a lot more interesting than just the plain time translation. And of course, we can permute and translate in pitch and time, and that's called a transposing round. I don't think, that's my term, but I don't think there's a better one. This is essentially the second great secret of Baroque music, right? Corelli discovered this, and boom, the Baroque exploded, right? Because it's a machine, it's an algorithm. You input one measure of music, and you get out, 6, 20, however many measures you want. So we can represent this with arrow notation here. We have some repeating musical cell. The arrows show where the notes go, and those T labels are transformations, translations applied to the music. These operations are well-known symmetries. These, in my paper with Cliff Callender and Ian Quinn, we call these the optic symmetries. They correspond to octave transposition. permutation, and then translation, all right? And applying each package of symmetries gives you a different kind of musical phenomenon: sequence round, transposing round. We have what I jokingly call the standard model of music. Our standard package of symmetries is octave displacements, permutations, transpositions, or translations. So Zn semidirect Sn, the symmetric group on n letters. In this case, direct product with the group of translations and pitch, which is R, or Z if you only want to stick to the keys of the piano keyboard. And now I'm just going to report on some recent work, which is a little bit of magic. This is one of those bits of magic where if you get the definitions just right, you end up with something that looks like 1 equals 1, a kind of triviality, but is actually sort of deeply revealing. So it turns out that, every left group action defines a corresponding right group action and vice versa. That's not obvious unless you get all your definitions right. This correspondence is equivalent to a bunch of different dichotomies that show up throughout music theory. The dichotomy between symmetries and intervals, between what we call absolute and contextual transformations, between operations that fold a groupoid or some kind of geometrical space, and loops or fundamental group elements through a quotient, which could be a groupoid or some kind of orbifold, the action by deck transformations and the action by lifting, for those of you who speak topology, and then permutations of musical elements like notes versus permutations of data assigned to those elements like the name of the instrument playing the note. So these are all manifestations of the same basic structure, and if you set up all your definitions just right, you can see that super clearly. The reason that's important is that in music, we have two different manifestations of our big symmetry group. We have its action from the left and its action from the right. L is the action from the left. R is the action from the right. And the L symmetries are cross-cultural universals. Basically, every culture has some version of octave displacement, has some version of taking the notes in a musical chord or idea or motive and permuting them, and has some notion of transposition. Now, it turns out that these operations have their duals. These operations can be seen as symmetry operations that fold up some space. They have duals as paths through a quotient space, and those are R, voice exchanges, chordal transpositions, which earlier showed up when we were shifting those motives along the top level of the hierarchy, and something called Schritz, which we're not going to talk about right now. And the R versions of the L symmetries are distinctively Western. So what's kind of interesting here, if you read a normal math textbook, they almost all say, well, left group actions and right group actions are the same thing, and so we're only going to work with left actions. We don't care about the right actions. But in the musical case, the two group actions actually suggest non-isomorphic group decompositions. So if you're thinking in terms of the L symmetries, they have a privileged symmetric group subgroup, but the R symmetries don't have that. Instead, they have a privileged Z subgroup, right? And that Z subgroup is the top level of my hierarchy. And so what's really interesting here is the idea that over centuries, Western musicians kind of went from this L way of thinking about music to the R way of thinking about music. So we're doing a kind of intuitive group theory without realizing that we were doing this. And so there are a bunch of paths where you can sort of slip from one way of thinking about musical operations to the other way of thinking about musical operations. And so this sort of hints at a kind of a deep historical explanation for how Western music became the way it is. The other thing that's really interesting is that this shift between two different ways of thinking about musical operations creates a link between timescales, because the R operations are local and basically characterize chord progressions, and the L operations can be applied to arbitrarily long stretches of music. So to illustrate that, here's a stretch of music. This is the C minor fugue from Bach's Well-Tempered Clavier, Book 1. I'll play just a little bit of it because Great stuff. So this is the whole piece here. Here is my analysis of the piece. On the left, I have its 1, 2, 3, 4, 5 basic patterns. Entry, sequence 1A, sequence 1B, sequence 2, sequence 3. And on the right, I have a little chorale, a little piece of music. Now, music theorists started producing reductions that looked like this, summaries of Bach's piece that took the form of little pieces of music. But it was not really clear what those summaries amounted to, how to justify them methodologically. There was a lot of bad philosophy that was created in order to justify them philosophically. The framework that I'm outlining to you allows us to say very rigorously that Bach's piece is this chunk of music over here times this chunk of music over here. And again, you can algorithmically recreate almost every note of the original if you understand the meaning of these two things. So what's cool is we're over here, these transformations are homotopy group elements. They're little chord progressions that are really, they make sense only relative to as directions for how to get from one chord to another, and then we can kind of take the direct product with these patterns, and so it's a link between two different ways of thinking about music. The way you might put it is the repetition group, the group that tells us what transformations we can do to big chunks of music, is isomorphic to the voice leading group, which is the group that tells us the group of allowable moves if we're sitting on one particular chord. And this isomorphism is just basically the well-known isomorphism between a symmetry group and a fundamental group, deck transformations, and the action by lifting. Every act of repetition is a chord progression. So we have these two different languages for describing repetition that are isomorphic in a mathematical sense holistically, but are musically very, very different if you're sitting at the keyboard. And that I think this isomorphism is the origin of the very notion of the chord and the hierarchical structure of Western music. So all of this has a super beautiful geometry in terms of orbifolds and quotient spaces, and I don't have time to explain that to you, so I'm just going to show you some pictures. In my book, I have sort of come up with I have this new book, Tonality and Owner's Manual, just published in November. Very technical, so don't buy it unless you're a musician. But I came up with these two-dimensional geometrical representations that basically describe an important class of loops through the higher dimensional configuration spaces that represent music. And what this allows us to do is model passages of music as involving self-similar motion on different time scales. So here's a celebrated passage from Beethoven's Ninth Symphony. And over here is a kind of representation of the configuration space of chords. And over here is a representation of the configuration space of scales. Those are the two higher levels of my hierarchy. And you'll see Beethoven is essentially making similar moves on those two levels. And then here is a remarkably similar passage by one of my favorite musicians, McCoy Tyner, jazz pianist, most famous for playing with John Coltrane. And he's actually doing a very similar kind of thing where he's moving systematically through chordal and scalar domains. I'm going to play it once with musical notation and then once with the kind of geometrical model. Probably more impressive than what Beethoven's doing because he's doing it in real time without any planning. This is what it looks like geometrically. This is a kind of deep structure of musical thinking. All right, so that takes me basically to the end of my talk. We have a picture of wheels within wheels, where what a huge range of Western musicians are doing, from Bach to the Beatles, is moving musical voices within possibly scale-like chords that themselves move inside scales, that themselves move inside a big collection of possible notes. There's a very simple organizational strategy that generates music of extraordinary psychological complexity. It is really hard to manage 3 separate levels of motion along a collection, particularly if you're working with unfamiliar chords and scales. For analysts, it can be really hard to recognize these structures in pre-existing music. It's hard for humans to do, and it's even harder for computers to do, especially if the computers aren't told what to look for. And this is an opportunity for theory, mathematics, concept thinking. It's a way we can be of service to music making. We can generate compositional assistants, algorithmic helpers. And then, just on the very sort of practical level, there is this possibility of making music at different levels of the hierarchy. And this is something that both classical composers and improvisers are quite aware of. Improvisers sometimes move between improvising relative to the specific chords of a tune, which is at the top level, and then stepping back and more holistically playing scales and leaving the chords alone. And in the classical tradition, that's sort of the difference between traditional tonal music and what's sometimes called pandiatonicism, which is an innovation that's associated with Debussy and Stravinsky. That is the end of my talk. Thank you very much.
So perfect timing, and okay, Andres went up first.
I have a comment and a question. My comment is you very interesting talk. A little too fast for me, but I'm a slow person. The comment is that you talk about quote unquote secret of the Baroque music.
Yeah.
Of course, within these transpositions and various other mathematical forms of transforming melodies, composers have a lot of choices, which of them they use and which they don't use.
Yeah.
And importantly, they have a choice of the motif that defines the whole thing.
Yeah.
And the best proof that there is a huge richness in possibilities. I'm just pushing back a little bit that, the secret is out. Is that you can tell Corelli from Vivaldi. If you've listened enough, you will be able to tell that Corelli is different, even though both of them use similar tactics as you've described. My question is very, very down to earth. I didn't understand this. I think it was in Bach example was well-tempered clavier. Where the multiplication. What kind of multiplication are you talking about?
Right. Okay. So, but I want to respond to the first part, which is that. So you're absolutely right that human choices bear the mark of the choice maker, right? I think the interesting question, so let's take, I make a melody, you make a melody. If you listen to 1,000 melodies by me and 1,000 melodies by you, you probably will come to be able to recognize the difference. So there's nothing, I don't want to say anything against that. So personality is all over our productions. I'm a little bit maybe, and this is something I was talking to someone else about in coffee break, I'm a little bit prepared to push harder on the idea that Vivaldi's choices are better or worse than Corelli's choices, or even that Bach's choices, are better or worse than Vivaldi's. Like, it feels to me, I personally think that when we think about music, I've come to think we overvalue the question of individual quality and we undervalue the question of systemic quality. So I think that's an interesting sort of concept, and that's a place where I would like to say, yeah, it really is the secret, because Schubert made different choices from Beethoven, but if you learn the secret, your choices, and you didn't make dumb choices, so you have to go through some period of training. But if you learn the secret and were trained for 5 years, your choices would be as good as Schubert's and Beethoven's. And it is the secret in that what's really generating the incredible quality is the system rather than the specific taste of the choice maker. So that's an interesting, I can't back that up. I can just say that's sort of where I want to be going here, is to, and partly this is because I write computer algorithms that make these things randomly, right? And I think, boy, you know, if 25 lines of code can do that, 5 years of training is going to do significantly better. And so yeah, that is an interesting way to go. So in terms of the, you know, you probably have to read, I don't know if I can, so basically this chord progression here is a set of directions for, so basically you'll see each pattern has some white notes there, like pattern 1 has 3 notes. Entry up there at the top has C, E flat, and G in white, the second to last 8th note of the measure, right? So when you see entry there and entry there, that chord progression is a set of directions for transforming the white notes of entry, which then can give you this set of transformations for the rest of the notes.
What's so special about white notes?
Oh, nothing. They're just arbitrarily chosen. But the point is that people like Schenker started producing these kinds of reductions of things like Bach, right? And they did not, and so what they were doing is they were essentially analyzing large passages of music, reducing them to little pieces of music, right? And so the point is that this actually gives you an algorithmic reconstruction of that practice. And what it specifically allows you to do that's compositionally relevant is you can take any voice leading. So you sit at the piano and play 2 forms of the same chord, right? And it allows you to translate that voice leading into a sequence, basically through this multiplication technique. Now, like a lot of math, this is something that becomes obvious once it's pointed out, but before it's pointed out, we didn't know how to do it. And so it's actually something that you can improvise. You can improvise sequences and patterns. You can take any voice leading, create sequences. This is something that absolutely should be part of our undergraduate education and isn't. I was talking to my friend Jordan Ellenberg, who's a mathematician, and he said the wonderful thing about math is a lot of it is really obvious, but a kind of obviousness that it takes you many years to see is in fact obvious. So this kind of relation between the local structure, the voice leading, and the global structure, the relation between these 10 measures and these 10 measures, is both obvious and non-obvious. And I think that Schenker intuited it when he started producing little maps like this and saying, this little piece of music, he'd leave out the left part, this little piece of music represents the whole chorale. And many people said, wow, that seems right. And yet, the justifications you find in the literature for that kind of compression don't make any sense. They're buried in Hegelian metaphysics. They're not computationally tractable. There's all sorts of problems with them. So. Yes? Oh, sorry. I'm trying to be my own monitor.
Great talk. I loved it. I worked in particle physics, and I was intrigued by your standard model of music. So, and this may be a completely ridiculous question, but have you thought about taking that further? Like, can you apply, say, Noether's theorem to the groups and say something about, you know, the music or
Yeah. Well, I mean, it's not Noether's theorem, but the Z subgroup preserves distances at the top level of hierarchy. Right, so any group has a subgroup of isometries, right? And so that is the subgroup of isometries when you're thinking in this hierarchical way. So all of these transformations preserve some kind of distance or another, and that preservation of distance, our ears are super sensitive to musical distance rather than absolute position in musical space, right? So yeah. Conserved quantities. This is all about conserved quantities. But I would say that L conserves one set of quantities, and that little Z subgroup actually preserves a totally different set of distances. So the kind of surprising thing here is you've got this group action, and it's preserving distances and you know exactly what it is, and then buried inside its right action dual is this other little subgroup that preserves a totally different set of distances. And in a way, the story of the 16th century in music is composers gradually becoming sensitive to that other kind of distance without anyone saying that they should or anything like this, kind of noticing these patterns from spending thousands of hours, you know, making music.
So, can I be selfish and ask a
Yeah.
question by being chair? So I was wondering if you have some kind of, you can with this, have this, you're looking at homotopy groups, can you build a moduli space of where, you know, certain composers like those together? I mean, this, I think you're saying, okay, Western music may place restrictions on certain parts of this standard model. You might have another group. Can that extend music? Can you discover new music that will sound radically different? Because it does seem extremely exciting, an exciting way for a mathematician to bypass decades of musical training and say, I'm going to discover a new genre of music.
Yeah, I probably shouldn't give that impression. Sorry. No Royal Road, folks. Okay, those are two separate, I'm going to answer them in inverse order. What I would say, so I am a composer. I spend a lot of time composing music. What I would say in terms of discovering exciting new musics is basically traditional composers learn how to manipulate this structure only with a small set of chords and scales. So we only know how to do it with basically the major and minor chords and the major and minor keys of Western tonality. And I have set things up so that it is completely neutral, so that you can, first of all, you can say, well, I want a 4-leveled hierarchy, and second of all, you can just choose whatever chords and scales you want. If you want microtonal scales, you can do that, right? And so basically, the goal of my second book and the goal of this whole project is to take the grammar of traditional music making and make it sort of collection neutral, so that we can make something that we can use those techniques in kind of whatever domains we want. Now, for me, I think that's plenty exciting. There's decades worth of really cool music to be made in that way. In terms of the analysis question of like, I would say we are probably not at the point where, so I would say this kind of hierarchical structure is necessary for giving any kind of coherent computational analysis of Schubert and Beethoven and Mozart and so on. And a coherent computational analysis of those composers is gonna, the way you can tell that it's doing anything correctly is that it's going to put make Beethoven and Schubert look similar, and Mozart and Haydn look similar, and both of those look more similar to each other than to Brahms, and so on. I don't think that the geometry and the orbifolds are really going to help that much relative to that same information expressed symbolically or algebraically or in something like this form. I mean, with all of this, there's a description in terms of, okay, you're at this point in this highly abstract configuration space, and then there's another description that uses kind of recognizable musical language. There are some cases where the geometrical description really adds content. You can say, well, certain phenomena are only possible if you're near a singularity in an orbifold, right? Like that gives you a kind of conceptual understanding that the musical terminology doesn't. But when you're getting to this kind of very fine-grained, high-dimensional comparison of Mozart, Schubert, and Beethoven, it's not going to be something like, well, it's not going to be something that the geometry is going to encode in a very clear way.
Exploring the singularities, can we find well, you could become the next composer of a completely new genre of music.
Yeah, well, there's only really, the singularities kind of go with the symmetries, and so we sort of know what they are. And actually, in my first book, I argue that the composer Georgi Ligeti from the 1960s did explore the symmetries, this symmetry here, and he was the first one to do that. And but okay, we only have these symmetries, and these symmetries are really kind of baked into our perceptual system, right? So one of the things that often happens is someone mathematical says something like, well, I'm just going to invent a new symmetry and use that to compose music, and the problem is that we don't hear it, and so you've just got this inert mathematics. I mean, the beautiful thing about all of this stuff is it's obvious to the ear in some sense, right? And so again, one way in which this enterprise of music making is different from mathematics is that it only counts if it's obvious to the ear. Anything else is barren.
Yes, question.
So kind of related to that, how does dynamics fit into this?
Yeah, that's a great question. So, I mean, I guess that the dynamics sort of, I would go back, and I do apologize, you know, guys, I live in my own head, and, you know, I'm like 15 years down this deep musical and mathematical journey, and I'm trying to, so don't worry about the details, I'm aware, I go very fast, and this all is kind of, it's not meant to be understood sort of at a granular level. The dynamics, I think, operate here, right, where phrases are constructed, say, by making a slow melodic descent, something like, you know, right, 3-blind mice, and then so you can think of that as having this buried inside it, right? So we're making patterns at these different hierarchical levels that are basically doing some version of stable and home, away and dissonant, back to stable and home. And so we're doing that at the level of the, you know, multiple times a second when you're at that top level, and then, you know, maybe once per piece at this bottom level. So that's where the dynamics come in, and that dynamics is largely guided by taste and personality and the kind of choices that Schubert makes or Vivaldi makes or whatever.
Okay. We're over time, but maybe we end the session, or are there more questions? Because I took up.
You are allowed to ask a question. You're a human. I'm available. So if you have questions.
Okay, so let's thank Dmitri.